Hello, and welcome to our next set of stats notes. Today we're covering section 5.1. Like I said in the previous video, we're kind of moving on now from probability, but we're actually going to keep having probability happen because we're going to mix probability back in with statistics. So this is the chapter where we kind of connect the two and show why we covered probability in the previous section. Because probability and randomness is definitely a big aspect of doing statistical studies and that kind of thing. Okay, so section 5.1, we're going to deal with what we call random variables, and then we're going to get into probability distributions. So when you think of variables, you probably think about algebra. In algebra class, we'd have a variable x that would just stand for a number that we didn't know yet, and then we try and find it all the time. In statistics, when we talk about random variables, we're more talking about a set of results, the different possible outcomes or results we can get when we do an experiment or give out a survey. We usually use a capital X for a random variable, and it's kind of talk about the set of all the different results we can get. So we'll have different single numerical values for the different results, but it's the outcomes we can get when we do a procedure, and then when it has some kind of elements of chance of things that can happen. So this is a random variable, so it's a numerical value, and we get the different outcomes from the procedure, and it's going to have some element of chance to it. These come in two different types, so there's two main different types. We're going to mostly work with a discrete random variables. That's when we'll see the rest of the section really. A discrete random variable has that word discrete. In mathematics, that typically means that they're kind of separate, singular entities. Like when you do your counting numbers, 1, 2, 3, 4, 5, those are discrete values because there's space between them. When you start thinking about decimals and fractions, that's where you're going to lose that discreteness because there's all those values between, like 1 and 2, like 1.5, 1 1/3, 1.5. Those are all numbers between 1 and 2. So this is either going to be finite, so it's going to be a list that ends. There's only so many options. If you only have 15, 20, 100 options, and then that's it. That's all your options. That's a discrete set because there's only so many things you can get. Or countable, and so those numbers 1, 2, 3, 4. They can go on forever. You can count forever, so it's not finite. It doesn't stop, but that would be a discrete set because there's space between each value. So things where you can simply count 1, 2, 3, 4, 5, even if you might be counting with like a decimal point 5. Like I think about shoe sizes, you can start with 1, and then you have 1.5, 2, 2.5, 3, 3.5. That would be a set that would be countable because you could sit there and count them even though you're counting decimals. But it's would still be discrete. It's something where it ends. So when you think about discrete, you definitely want to think about counting things. Things that you can count is the big part of it. So like the number of coin tosses. There's going to be so many coin tosses. The number of students in a class. That one's usually finite, right? Because there's not usually an infinite limit to how many students can be in a class. There's kind of the upper cap for the school or the university or whatever. Those would be kind of countable, discrete sets of information. The other type of random variable is going to be a continuous one. So a continuous random variable is something that's infinite, so it's not going to stop, it's not finite, so there's infinite many choices for what the value could be, and it's not going to be countable. Think about things that you would measure. Think about like weight or height. These are things where you can go out and you can get so many decimals and fractions, and someone could be 5'10", or they could be 5'10.5", or they could be 5'10" and 1/4. You can get more and more specific depending on how good your measuring tools are. So it's infinite, but uncountable. And that's going to be your continuous. Think about things that you measure. That's when you're going to be dealing with more of this continuous type results. So height, weight, temperature, how long it takes you to complete a task, that would all be continuous random variables, things that you measure. Really, you think about countable. Countable is not going to include usually fractions or decimals. Like I said, you can kind of have so many decimals or fractions if there's a limit to how many there are. If you only have the halves or just the quarters and that's it. But if you start getting too many options for your decimals or fractions, then you're probably moving into the continuous realm and not doing discrete. So let's look at a couple more examples. Just think of some examples. So some examples of discrete things. Anything basically that you can go out there and you can count it. How many credit hours a student has taken? That would be credit hours. That would be something you could count. You can count how many days off you get per year. days off per year. Because you're counting these. You know, these are things you're going to count. Number of pets, any number, anything you can go out there and count. Not measure, but count. So these would typically be whole numbers, right? You're not going to have half pets. You could have a half day, but you typically either have whole days or half days. Most workers, you take, quarter days. So there's going to be only so many options. Only up to 365 days a year. There's a limit. Credit hours, you can only take so many hours per semester. Eventually, you get to the point where it's just not doable. You can't do that many classes. Continuous again. Continuous. Think about measurement. Right now it's storming outside. It's raining. So rainfall, because you go out and you measure how many inches of rain happen. That would be a measurable thing, not a countable. I can't count the number, or I can't count the amount of rain. Other things that would be continuous might be the length or the distance from you work from home, from home to work. That would be something you measure. You go out there and measure how far away your home is from work. So you measure that. That'd be a measurable, continuous type variable. Brightness of a star. So anything that you measure, that's going to be continuous. We're going to mostly focus on discrete variables in this section. We're going to keep kind of things more simple because we're going to work on this discrete where they have individual values and we don't have like these range of measurements. So that's where we're going to put our focus. So we're going to want to display discrete random variables, these finite or countable sets, where things are counting, not measuring. We're going to use what we call a probability distribution. So probability distribution is a way to present all the different results that you can get for a variable, and then the likelihood of those different results. So we're going to use a probability distribution. We use percentages or probabilities, and this is something you'll see the rest of the semester. Percentages and probabilities, there's a strong relationship there. If you go out and do a survey and find out that 50% of people you surveyed are looking for a better job, then the chances, the probability that one of the people in that group you were surveying is looking for a better job would be 50%. That'd be that experimental probability that that we talked about earlier, where you go out and do a study or do a survey. So percentages are going to be directly related to probabilities from now on. That's something you'll see a lot in statistics. Is a percentage is a probability. The percentage of people that have this characteristic, well, that's the likelihood that if you picked a person at random and have that characteristic. So percentages, probabilities, we'll use those pretty interchangeably from here on out. For all the possible values of a random variable. So we said the random variable can have the different results. So we're going to look at all the different results it could have and then create a table, formula, or graph to give that probability, and we'll call it a probability distribution. So it's a table, formula, or graph gives the probability for each value for all those different values that this variable can have. So that's for the discrete random variable, and call it probability distribution. We're going to use that P of X to denote the probability. Remember that P instead of in front of the parentheses is the probability of X. So we're going to look at the probability of each result, where X is the different results, the different values that the variable, the random variable, capital X can have. So here's an example. This is a probability distribution. Probability distribution, actually it's not, sorry, I should say this is a frequency distribution to help us make a probability distribution, because probability distributions have the percentages. This has a frequency. Remember, frequencies are counts, so this is just the counts. So this is a chart showing the number of siblings from people surveyed. So there's 8 of them that had 0 siblings, 17 that had 1 sibling, 11 that had 2 siblings, 3 that had 3 siblings, and 1 that had 4 siblings. In total, they surveyed and talked to 40 people. So there's 40 people who are surveyed, and this is the frequency data they got from that. So to make a probability distribution, we're going to find the probability of each of those values, the likelihood for each of those values, and fill that chart in. So for example, what's the probability that you have 0 siblings? Well, there's 8 out of the 40, so 8 out of 40 have that. So I just pulled my calculator, divide the 8 divided by 40. And we see that the probability is 0.2, or 20%, if you put the decimal 2 spots. So there's a 20% chance you're going to have 0 siblings. For 1, that was 17, so 17 out of 40. 17 out of 40 gives us 42.5 even with that decimal 2 spots. So you get 42.5, so almost half, right? Almost 50. 42.5% have one sibling. Two siblings is going to be 11. So we're going to take 11 and divide it by 40. 11 divided by 40 for the two siblings. We see that's 27.5. So 27.5% is the percentage of people that have two siblings. Three siblings, there's only three of those. So 3 divided by 40. 3 over 40 gives us 7.5%. So 7.5% is the percent that have three siblings. And then four siblings, there was only one of those. So if we do 1 divided by 40, last one we get 2.5. So 1 out of 40 gives us 2.5%. So 2.5% of these people have four siblings. So these are the probabilities. This is a probability distribution, so it's showing the probability or the percentage of each of these different results. So for this result of having no siblings, 20% of people have that result. Well, 42.5% had one sibling. 27.5% had two siblings. So if I go pick a person at random and say, what's the likelihood they have four siblings? I'll say there's a 2.5% chance they have four siblings. Or what's the chances they have zero siblings? There's a 20% chance they have zero siblings. Couple of things about this. So first off, the variable x to make a probability distribution has to be numerical and not categorical. So you'll notice that these are going to be numbers. These are going to be counted values. They're not going to be categories. So not categorical, variable x is numerical. So if you make a set of data with categories, you can't make a discrete random variable probability distribution with it. The sum of the probabilities is 1. So if you look at these, if you add these up, if you add up the 20 plus 42.5 plus 27.5 plus 7.5 plus 2.5, you get 100%. So this does total. The total should be 100%. You know, if you're rounding, you might end up with something where it ends up being like 99 or 101 if you did enough rounding or something. Here, I picked numbers that didn't round too much, so I was safe. I got a nice 100%. But if I was doing a real-life example, you might end up with enough decimals here where you might round up or down enough to get a 101 or 99, but it should be pretty close to 100%. If you're getting way above 100 or way below 100, then you know it's not good. You know, if you get 95 or 105, then I'm going to say, oh, that's not right, something's wrong here. But it should be pretty close to 100%. So the sum of the probabilities is 1. Remember that 1 is the same thing as 100%. So, or 100%. Another way of writing this is that the sum of probabilities is 1. Remember that we use this notation for sums. That's your probabilities of the different values. And so the sum of those probabilities should be 1 or 100%. Other thing, the probabilities, each one of these different probabilities should be between 0 and 1. You should never get a probability lower than 0 or above 1. So 20%, you know, is 0.2. It's between 0 and 1. So this is like the same between 0% and 100%. So it should always be between 0 and 100%. So that should always be true for each probability. It should be between 0 and 1. And that makes it a proper probability distribution. If you're trying to make a probability distribution, it should look like this. You already have your different values that you could get. These are the results. You can have more or less. Here we only went to 4 siblings. Maybe the study we didn't find anybody with 5, but maybe you had someone with 5, and you might have an extra number down at the bottom that goes all the way to 5. If you have someone with 9, you go all the way down to 9. And then again, these should all be percentages or decimals. You know, you can write this as a decimal, so percent, but these are showing the probabilities or percentages for each one of those values, and they should add up to 100%. So the next page, I got a couple examples. I just want to determine, are these actually legitimate probability distributions? First thing we look for, probability distributions, are we using numerical or categorical? Well, first off, these are numbers. This is numerical, so we're good to go. You know, we're not looking at categorical data, so that checks off. We're good. Next thing, all these values should be between 0 and 1. So these values, x's are the probability of each x is between 1 and 0. And it could be equal to. It's okay for one to be equal to 0 or equal to 1. So, but that checks out. So those are good. Last thing to do is we've got to check, make sure that you add them up. They do to add up to 1. Do get 100%. So if I do 0.02, that's 0.03, that's 0.1, that's 0.45, that's 0.5. Should add up, and I should get. Ooh, I don't. I get 1.1. Now I said, 101 is okay. This is like 110, right? Because if we turn this to a percent by multiplying by 100, this is 110%. That's way off. This is too high. So the total, the sum of the p of x's is equal to 1.10 or 110%, not 100%. So no, this one is not, because the total is too big. You get more than 100%. You can't have that much more than 100%. Like I said, if you're really close to 100, you might have some rounding. But this one, that's more than just rounding. They have an extra 10%. That's way too much. So this is not a valid probability distribution. It's not just rounding error. They didn't do their calculations here right. Next one, again, first thing we look up for is it numerical or categorical, and these are categories. They're not numerical values. These are categorical. They're labels. So if it's categorical data, it's not a proper probability distribution. We're looking at numerical stuff. So this does not work. No, it needs to be numerical. So it has to be numerical data, or otherwise it doesn't really make sense to make a probability distribution out of it. Okay, last one. Okay, again, this is numerical, so we're good there. We're looking for numerical. These are numbers. So that works. I look at each value. Is it between 0 and 1? These are all decimals between 0 and 1, so yes. 0 is less than or equal to the probability of each value is less than or equal to 1. Checks out. And then again, the last thing we check is we just want to make sure, do they add up to 1? So if I add these up, do I get 1? So I should add up my values. And I get 1. So the total, the sum of the probabilities is 1, or 100%. That checks out, so it passes all three parameters. This is a proper probability distribution. So yes, this is a probability distribution. So this could actually reflect a real set of data. So maybe this is like the number of hours full-time students are taking, and all the students are taking somewhere between 15 to 20 hours out of the group you sampled, and that would be a legitimate, possible set of results. Maybe they can't do less than 15 because that would be not full-time. So if full-time is 15 or more for this university, that would be a true, proper set of results that would be possible. Okay. Now, probability distributions are usually given to you without the actual data. A lot of times people will figure out the percentages based on a survey. Pardon me. Sorry, I had to cough there. So they'll go out and they'll collect data. They'll do samples and they kind of develop a set of data where they know the percentages of certain aspects. And they'll take that data and they'll present it to you and say, okay, I don't know the exact numbers of people that are this or that or whatever, one sibling, two siblings, three siblings. But I know in this, country or whatever, this is the percentage, because we did a survey and we kind of figured out about what the percentages should be. And so we can give you that. And so a lot of times you'll be given this data to represent an entire population. They'll use this data to show a whole population. So probability distributions represent an entire population. And so we'll use this to calculate parameters. Parameters such as the mean, the standard deviation, and the variance. Remember, parameters are just a way of measuring values or information about an entire population. So you can look at the average, the mean, and look at the spread of the population. So how much spread is there in this data? Do your standard deviation. Remember, variance is another measure for spread. We don't really worry too much about variance because remember, variance is just the square of standard deviation. And also, variance gets a little complicated. So we're not going to see a whole lot of it here. In this section, basically, we'll just say, yeah, if you have the standard deviation, just square it. There's the variance. It's not too much different. So we can actually calculate this. If someone gives you the discrete random variable, so that is that probability distribution, you can use these formulas to calculate these values. You can calculate the mean by doing this, where you're going to take the sum. Remember, that means sum of all the values. You can actually take the number for each value. This is one reason why they have to be numbers, because you can't calculate this if they were labels. The value of each number times its probability. So you're going to multiply what the value is times its probability. So like if there's one sibling and there's 45%, it would be 1 times 45%. So if 45% have one sibling, that'd be the idea. And then you multiply all those and add them all up, and that'd be the mean, the average. The standard deviation, in this case, you're actually going to square all the original values. This is one thing, again, we'll do that first. We'll square the value, multiply times probability, and then we'll actually subtract the square of the mean, and then take that whole thing and square root it. And that's the calculation. This will give you the standard deviation. So this is the way to find the spread. Again, we're going to be adding up and doing all that kind of stuff. Variance is just this same thing squared. So you see how the square root is gone? Because if you square square root goes away. And so that's the same thing as the standard deviation, just squared. And so that's why it's not a big deal, because once you have the standard deviation, you just square it to get this the variance. Or you could just not square root it in the first place, and that is the variance. Now, these do have computing formulas. So if you're a statistician and you're writing a computer program and you needed to calculate the mean, standard deviation, variance from a probability distribution, you would use these formulas. The mean ones actually doesn't have its own. So the mean, we just use the way we did, because that one's pretty straightforward. These other ones, these computing formulas, the reason people have these and the reason why they can be important is because they avoid rounding. And so if you're trying to write a computer program and you want to get rid of as much rounding as possible to get a more accurate answer, then you'd use these formulas. If you use technology, it's probably already got these formulas built into it, and we'll talk about that on the next page. So this is something we're not going to worry too much about, because once we get to technology, we really don't need to worry too much about these formulas, because the technology will kind of cover these for us. But that's what these are. Computing, there's less rounding in these nice computing formulas. So if you're worried about trying to get more exact answers, again, we're just doing stats, intro to stats. We're not doing advanced stats. So we're not really going to worry too much about that. We'll be fine just using these for now, and then using programs in our calculator and stuff later. So first off, we're going to do this. We're going to take this probability distribution I have down here, and we're going to calculate the mean, the standard deviation, the variance. So we can show you how you can use these formulas to calculate that. First one, to do the mean, we need to multiply all these values times the probabilities. So we get each value and multiply times the probability, and then I'm going to just fill that in here. I left myself some space here. So I do 0 times 0.029, well, that's going to be 0. That one's pretty easy, because 0 times anything is just 0. 1 times 0.049 is going to just become 0.049. When you multiply times 1, it doesn't change. Now 2 I'm going to actually do, because I don't want to do this in my head. So I'm going to do 2 times 0.078, and that gives me 0.156. 3 I'm multiplying times 0.155, so I get 0.465. 4 times 0.212 gives me 0.848. 5 times 0.262 gives me 1.3. And 6 times 0.215 gives me 1.29. Okay, so these are the values we get when we multiply the value times the probability. Basically, the way to think of this is you're kind of weighting each of these numbers, these different results, by what the percentage is. So the higher the percentage, the more that weighs. Of course, the bigger numbers are going to get bigger just because they're bigger values, but you're kind of weighting these. And so then the bigger the percentage, the more that number is going to weight. And so then when you add these all up, you'll get close to the average, the mean, because you've weighted the numbers by their values. So I'm just going to add those numbers up that we got. This is the fun part where you can just type some numbers. That's one thing with stats. We work with so many numbers that a lot of it, the time can be spent sitting there just typing values in a calculator. Okay, typing those in, 1.3, hopefully I got them all typed in correctly, so I always go back and double check. So 1.29, 1.3, 0.848, 0.465, 1.56, 0.049, and 0 we don't have to worry about because it doesn't change anything. So adding those all in, I get 4.108. So 4.108 is our mean. Because again, we said the mean is just multiplying those values and then adding them all up. So that's the mean, 4.108. Notice that the mean is, somewhat in the middle, right? It's a little bit closer to the 6 than it is the 0 because we see that there's higher percentages down here. So these bigger numbers end up being weighted a little bit more. So I ended up taking this number and shifting it. So we're kind of on the high end instead of the low end. Now, 3 is right in the middle between 0 and 6, but because these numbers have less weight, these numbers are a little bit more weight, we end up moving down. And so we end up with the average being closer to 4.108 than it is to 3. Okay, that's the mean. That's all you have to do to find mean. To find the standard deviation, we are going to have to do a couple things. First off, we need to square all the x's. So we're going to take each value, all the different results, and square them. Well, 0 squared is 0, 1 squared is 1, 2 squared is 4. When you square each, multiply times itself. So 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. That was the x squareds. And then we're going to multiply those times the p of x's over here, these p of x's. That's the next part. X squared times p of x. So I do 0 times 0.029, that's still 0. 1 times 0.049, that's still 0.049. When I do 4 times 0.078, we get a different result. So 4 times 0.078, and we get 0.312. So 0.312. I'm going to do the next one. So 0.155 is going to be multiplied by 9. So I get 1.395. I have 0.212 times 16. This gives me 3.392. And I have 0.215 times 36. Oh, did I miss one? Ooh, I'm trying to skip one. Let's go back. Let's do 0.262. Make sure I'm doing them in order. 262 times 25. And I get 6.55. Okay, then I do 2.215 times 36. And I get 7.74. Okay, so that's our squareds, our x squareds times our probabilities, p of x. We multiply those. Then we need to subtract the mean squared. So we need to figure out what the mean squared is. We know the mean is 4.108, so we're going to square that. So I'm just going to use my squaring button. There's a squaring button right there. There we need to square stuff. And that gives me this number, 16. I'll do 8. Let's go 88. Again, the more rounding you do, the less accurate you are. So if you want to be really careful, you would do a little bit less rounding. But that's I'm just doing, what's convenient for me right now. So 0.88. When you use technology, it kind of avoids that rounding in the first place. Okay, so we got mean squared. Then we need to subtract the mean squared from all those. That's the last part here. Subtract this mean squared. I didn't really leave myself space for that. I don't remember why I didn't leave myself space. I should have, I guess, but I don't know what I was thinking. So I didn't leave myself room. So I just get to try and fit it in here. So I'm going to fit it in here at the end. So the difference, just make room. And this is why people don't usually do this by hand, because it gets to be time consuming. But I get to do it by hand just to show you one. So I'm going to. Okay, so I'm going to take these values, I'm going to subtract. So this first one I get negative 16.88, because 0 minus anything, you just subtract it. 0.049 minus 16.88 gives, let's try that again because I didn't get the 6 in there. 49 minus 16.88 gives me negative 16.39. 0.312 minus 16.88 gives me negative 16.568. 1.395 minus 16.88 gives me negative 15.485. 3.392 minus 16.88 get negative 13.488. And then 6.55 minus 16.88 negative 10.33. Last one, 7.74 minus 16.88, and I get negative 9.14. Okay, so I'm going to add these all up. Make sure I get that right. Oh, that's why I made a mistake. I made a dumb mistake. It's been too long since I've done this section. So I made a dumb mistake because what I need to do is I actually just need to total these. I don't know why I did this whole thing. I tried to look back at my notes and forgot that what I'm supposed to do is just total them. You total them first, and then you subtract. So that's what you should be doing. You should be totaling and then subtracting. I'm not following my order of operations. No wonder this was going to be longer. 0.049. I'll show you in a minute why I don't really remember how to do this, because I don't do it very often, because thankfully, eventually we'll just figure out how to make our calculator do all this work for us. So that was kind of where I was getting with. I just want to show you one time so you kind of appreciate what your calculator is doing when you do this by hand. So if you add this up, then you get 19.438. Then we subtract the 16.88. and we get 2.558, which is the variance right now because we didn't square root anything yet. And then the last thing we do is we'll actually square root that answer, so 2.558. When you square root that, you get the standard deviation, which is 1.599. So that's the idea. So you can do all that by hand, and you can get the mean squared you use to get these two. It's not really important to find except for getting the variance and the standard deviation. Remember, this is the variance, and this is the standard deviation, and this is the mean. Again, we're using these symbols, which we talked about before. This is the Greek letter mu for mean, sigma, lowercase sigma for standard deviation, and sigma squared is your variance, because that's the relationship between these two. You square this one, and you get that one. Okay, so that's doing it by hand, which thankfully we are not going to do really any more than this one time, because it's a big, long, painful process. And this was only with like 7 options. If you have a set of data where there's like 10, 12, 15 options, it gets to be more time consuming. And we were being very precise because we were doing a lot of rounding. So the more rounding you do, you're going to lose a lot of precision. So instead of doing it this way, we can actually make the calculator do it. So let's do another set. This is a new list. But this time, instead of doing it by hand, we're going to find the mean, the standard deviation, and all that using a calculator. So to do this, we're going to put these in our lists in the calculator. So I'm going to make the x values, the actual values that we're getting, is list 1, and then the probabilities is going to be my list 2. So remember, to get lists, you're going to hit the stat button, and you're going to make sure you're on edit and hit enter. And this is where you can enter into your lists. So remember, we're going to use stat, and then edit, and then we can enter our data. So in list 1, and my data is going to be 15, type enter, 16, enter, 17, enter, 18, enter, 19, enter, and 20. So just hitting enter after each one. For my next list, I'm going to arrow over. Got point 15 for the first one, point 14, point 20, point 22, point 17, point 12. And again, those should line up because these line up. So if you ever end up with one list longer than another when you're doing this, you messed up, you missed a number or put in too many numbers. Once you have that in there, we're going to actually go back to that handy 1-bar stats. We're going to go to calculate and 1-bar stats. And then we'll do stat calculate 1-bar stats. So what we'll do now is we'll use this 1-bar stats, which we used before, and we'll leave list 1 as our list 1. But now, because we actually have a frequency list, now it's not a frequency, it's a probability list, but it works just as well. For this frequency list option, we're actually going to put that as second list 2. So remember, you can hit the second button, and then you can type these list buttons. There's list 1, list 2, list 3. So we're going to type list 2, so that the frequency list shows list 2, and that'll actually use these probabilities percentages to get our correct answer. So when we do this, our list, this should be list 1, so list should be list 1, and our frequency list should be list 2. And then after all that, I'll hit calculate, and now it will give me values. So now these values, the means and stuff, they're not just the mean of these numbers, but the mean of these numbers using these probabilities of these percentages. So now I can see that the mean for this is 17.48. So the mean, let's use X bar right there, is 17.48. The standard deviation, we're going to use the sigma. So you see this like sigma X right here. That's your standard deviation. It should be 1.557. So standard deviation, sigma X. That's the 1.5778. And again, you'll round to whatever my stat lab tells you to. That's what you round to. And then the sigma squared, that's the standard deviation squared. That one is not on here. They don't give you the standard deviation of the variance, which is the standard deviation squared, but that's okay because remember, you can just take the standard deviation and square it. So I just take that 1.5778 to the second power, and that's how I get that. So it becomes 2.489. So again, I'm going to take this square to get the variance. And that's what you're looking for. They wanted to find the mean, standard deviation, variance, and so we just did it with a calculator. And you can see why I wouldn't do that by hand unless someone like twisted my arm and made me, because it was so much easier just to type the data in the two lists and throw it in there. And it's, if you're in a work setting, not on a test for like our class, you can do all this stuff actually in like Excel and programs like that too. They all have these like built in, so you can calculate things like mean, standard deviation, variance. For our class, we're going to use a calculator on the exams since the calculator can restrict what you can do. You can't message and stuff. So you should be ready, on the test, you should be ready to take a probability distribution like this where they give you the different results and their percentages and probabilities, which you'll know they're probabilities because they'll be either labeled P of X or because you can tell they're all decimals or percentages. And they should add up to 1 if you double check. You know that in that situation, you're going to use that 1 bar stats, but you're going to make that list 2 be your frequency list. That's the big difference when you're doing 1 bar stats with the probability distributions. Versus if I just give you a set of data and to ask you to find the mean, well then you wouldn't have to have list 2 as your frequency list. So that's kind of the big difference versus when we were finding mean earlier in the semester. Okay, let's do one more set. So same thing here. Again, they want us to find the mean, the standard deviation, and the variance. So again, we're just going to put this data into our calculator and let the calculator do it for us. We'll make the top set of data list 1, bottom set of data list 2. That way our values are still list 1, right, because these are different possible results, and our probabilities are still list 2. That way when we go to do our 1 bar stats, we'll still have our list as L1, and then our frequency list will be L2. And that's kind of why we're doing it, it's similar to, so that when we go to that point, we don't have to change anything really. Okay, so I'm going to go back to my stat, hit edit. Now I want to clear these out, so remember, don't hit delete because it will get rid of the list and makes things complicated. I'm just going to hit clear and then enter, because that's the easy way to clear these. Hit clear and then enter. You don't have to clear them, you could just type over top. I always like to start fresh because that way I don't accidentally end up with an extra number or anything. Okay, type in my values. I get 0, 1, 2, 3, 4. My values, type in the probabilities, so the percentages, so I get 0.0882, 0.2252, 0.3125, 0.2844, 0.0897. Okay, so those are my percentages and my values. Again, they should match up, be the same length. That means you're doing it right. And I'm going to hit stat, calculate, 1 bar stats, not the 2, 1 bar stats. And again, list 1 is my data, list 2 is the percentages, probabilities. I hit calculate, and there we go. It gives us the numbers we need. That's the nice thing. I don't have to do anything more than that. So it just tells us that the mean is 2.0622, sigma x, which is your standard deviation, is 1.1033, and then again to find the variance, which is the sigma squared, we just take that number and square it. So let's quit out of this and hit 1.1033 and square, and that'll give me my value. So it's 1.217. So those are the numbers we're looking for. Again, this is your symbol for mean. You can use that for mean. We use this, and they kind of, at this point, we're kind of using it interchangeably because the calculator just always uses this for mean. Remember, this is population mean, and we're dealing with the population in this situation because we're dealing with all the possible values and the percentages of each value. So again, that's the mean. You should know that sigma is the standard deviation, and the sigma squared is the variance. That's what we're looking for. We're finding the mean, standard deviation, the variance. Okay. One more thing to talk about in this section, kind of important, is what we call expected value. So when we're doing means for discrete random variables, when we have these probability distributions, we find the mean. It's actually an important value. It's actually the theoretical average outcome. So it's kind of what you expect to happen if you do infinitely many trials. So if you sit there and survey people over and over again, and you're looking at the number of siblings, the mean we found for the number of siblings part was going to be your theoretical, like what you should find on average, people say, is the number of siblings. Another name for this is the expected value. So expected value, in the sense that it's the, that's the theoretical average outcome for infinitely many trials. So if you try this over again, it's the mean, the expected value is. Idea that if you were to repeat this, if you do it over and over again, infinitely many times, or even just a really large number of times, you expect to get that as your mean, your average of all your results. So if you go out there and you survey and you say, all the people, how many siblings you have, your average number of siblings that they answer would be the mean in this case, would be the expected value. So in real life, we often use the expected value, it's the name for it, to calculate the return on an investment. This is actually something we do all the time in real life. People look at the expected results from a game of chance, like a raffle ticket, and they figure out, okay, what's going to happen using the mean, and finding the expected value, and that gives them an insight into the game. So say you have a raffle ticket that's sold for $5, so that's the cost of the raffle ticket, and it awards a grand prize of $200, so there's only a single grand prize of $200. There are 2 first place prizes of $100 and 5 runner-up prizes of $50. What's the expected value if 300 tickets are sold? Okay, so to do this, let's make our own probability distribution. We're going to go ahead and make our own chart. We're going to have our values, so basically the x, the results, and we're going to have the probability of each value. What's the probability likelihood of each value? So first off, I think about my results. Well, if I'm really lucky, I win the grand prize, right? So if I win the grand prize, I make $200. But you gotta be careful. You have to subtract the cost. Because if you're gonna play this game, you don't get the tickets for free. You have to pay $5 for the tickets. So you play the game, you get $200 if you win, but you only actually end up with $195 because you spent $5 on the ticket. So your value for the winning prize, the grand prize, is actually $195. You always have to think about how much your net, not your profit, your revenue. This would be your profit. If I pay $5 for the ticket and I make $200 off the ticket, I actually made $195. And then you think about what's the probability of that happening. Well, since there's only one grand prize winner and there's 300 tickets, the probability is 1 in 300, which you could turn into a decimal. If you want to divide that out, 1 divided by 300. And that gives you a decimal. This one's not very fun because it's 0.003 repeating. So you'll actually see, we'll show you, you can actually type them as a fraction if that's easier. That's a nice thing. We'll type this in a calculator and do it as a fraction. But you could get a decimal if it's nice. Next thing, there's 2 first prize tickets of $100. Well, if you pay $5 for a ticket and you win 100, you only make $95. That's the second option if you're one of the first place prize winners. And there's only 2 of those out of those 300 tickets. So 2 divided by 300, which is, again, not a nice number. It's going to be 0.0606006 repeating. That's what you get when you divide by 300. It gives you some yucky numbers. Again, I'll just use fractions when I type in the calculator. Next one, 5 runner-up prizes. So there's 5 prizes for $50. But if you spend 5, you only make 45 because you spent 5 to get the prize. And there was 5 of those, so 5 out of the 300 are these runner-up prizes, where you get $50, but you only get 45 because you spent 5 to get it. And if I divide that one, 5 divided by 300, I get 0.016 repeating. Okay, now that's not all the options, because that's only the prize options. There's also the option that you bought the ticket and you didn't win anything, right? You could buy a ticket and it could be a loser. So there's always the possibility, the option of losing when you play a game of chance like this. And you want to make sure you include that. And to show that it's losing, we're going to put a negative. So this is going to be negative $5 because everybody that buys a ticket and doesn't win any money, they just lost $5. Now that's not everybody because we had those people that already won tickets. So when you do this one, you're not going to do that 300 out of 300. We're going to take and say, okay, how many people lost? Well, if I take 300 and I took away the 1 grand prize winner and the 2 first place prize winners and the 5 runner-up winners, take away what's 6, 3, 8, take away 8, I'm left with 292 non-winners. So that's actually how many people are not going to win. That's the number of losing tickets. So you always want to make sure you include this option, because if you just include the winning options, you're not really finding expected value because you're just finding the possible like rewards part. But when you buy tickets, it costs money. So if I do 292 divided by 300. Again, I'm trying to get some decimals, so I get 0.973 repeating. Okay, So now to find the mean, what we're going to do is we're going to type this in our calculator. We're going to do that list 1, list 2 again. So it could be our list 1 and our list 2. So I'm going to go stats, edit. I'm going to clear these out. I don't want all that stuff in there, so I'm going to clear. Into my 195, my 95, my 45, my -5. Make sure you use this negative button down here when you're doing this. Use that negative button to get the -5. If you try to use the minus button over here on this side, it's not going to know what's going on because it wants a negative. So I want -5. And then on another one, I'm going to do 1 divided by 300 because that's going to save me from doing any rounding. So I can type it in like that. And you'll see it gives you the decimal, but it's going to actually be more precise than it looks. So this is a good way to do it. Type in 2 divided by 300, 5 divided by 300, not 300,000, but 300, and 292 divided by 300. And there we go. So now we got the same length, this, so that's ready. And then we just hit stat. 1 bar stats. Again, go to calculate, do 1 bar stats. Make sure you have list 1, list 2, because frequency and percentages should always be list 2. Calculate. And there, the very first number is your mean. So the mean for this one, from a 1 bar stats, the mean is -2.83. This is what you call your expected value. And what this tells you is that if you go and you play this game of chance, if you go out and you buy a bunch of tickets, on average, this isn't per ticket, this is on average. On average, you should expect to lose about $2.83 per ticket. Now, you can't really lose $2.83 on one ticket because you can either make money or you can lose $5. So one ticket you buy, you probably lose $5. But since there are some winning tickets, if you go out there and buy a bunch of tickets, you can say, okay, well, on average, this is what's going to happen. I'm going to lose $2.83 per ticket. So this is expected value. It's the idea of kind of knowing on average what happens with this. This is what people use. If you go to a casino and play casino games, every casino game has an expected value. They're typically negative like this because usually you play the game and you lose money. The casino makes money. That's why casinos are open all over the place, because typically when someone goes in and plays a game, they lose money and the casino gets the money. And then the amount of expected value, how negative it is, actually fluctuates from game to game. The rule of thumb is that the more expensive the casino game, the more negative the expected value can be. So the more losses you'll expect to have. The best expected value is going to be on the cheapest games, but even then it's still negative. On average, the casino is always going to make more money than you are. Yeah, you can always beat that one person that gets lucky and makes a jackpot, but you shouldn't expect that. Because you should expect on average that you're going to lose money because the casino is making money, not you, on these machines. So that's expected value. It's a really important way to think about what happens when you play a game, the result. There's actually this famous story about, I believe it was MIT students who were looking at different lotteries, and they found this one weird situation. It wasn't regular. It was like it happened every once in a while in a runoff lottery in a certain state's lottery that they ended up with a positive expected value. It wasn't much, but it was just a little positive. It wasn't negative. And that was enough for them to go, wait, if it's a positive number, the more we invest, the more money we make. And they went out and bought millions of tickets, well, as much as they could. They actually got financial backers just to buy more and more tickets whenever this one situation showed up. And eventually, they were making good money, but eventually the lottery caught on. And so then they changed the rules so that never happened again. And they actually hire mathematicians and stuff just to make sure that that kind of thing doesn't happen, that the lottery always ends up with negative expected values for the players. So they're always losing money now. But that's something that happened back in the past. So you can use expected value to think about what should happen. You have to figure out the net value. How much am I making? Profit, not revenue, right? So I got $200, but I spent $5, so $195. And think about the probability of that happening. And then, again, we're multiplying all those and adding them up. But thankfully, the calculator does that part for us. So it saves us all that work. Let's do another example so you can kind of see this in action one more time. So here we go. We have playing a dice game at a casino. Pay $4, so that's the cost, right? If you're going to play this game, it's $4 to roll your pair of dice. And you win 20 if you roll a total of 7 on the dice. If you roll snake eyes, which is just a pair of ones, so both ones, then you pay an extra $2. That would stink. You lose, snake eyes pop up and you have to throw more money at them. You want to find the expected value. So again, the first thing we're going to do is we're going to think about the different possible results. So first off, play the game, you might be a winner, right? If you win, you win 20 bucks, but you already paid for to play. Don't forget to account for the cost. So you actually only win $16 because after you pay for it, win 20, you're up 16 bucks. That'd be the first option. Now I have to think about the probability. What's the probability of getting this to happen? Well, since you have to roll a total of 7, just think about how many ways you can get 7. Well, I could do like 1 and 6. That would give me 7. I can do 6 and 1. You know, if you switch the dice. I can do 2 and 5 would give me 7. So 5 and 2 would also give me 7. 3 and 4, and 4 and 3. I think that's it. You know, there's all my combinations. So I have 1, 2, 3, 4, 5, 6 ways. So 6 ways that you can get a total of sum of 7. So there's 6 of the options. If I roll 2 dice, again, we're going to say 6-sided dice. I always forget to write that down, but assume there's 6-sided dice because that's standard. How many different options can I get if I roll a pair of dice? Remember that gives me 36 outcomes because there's 6 sides on each dice, and that multiplication principle says if you know the number of options here and the number of options there, you multiply 6 times 6, you get the total number of options. So 36 options when you roll a pair of 6-sided dice, so we have 6 out of 36 is that first probability. You could simplify these if you want to. You don't need to because you can just type in the fraction for the calculator just like that, just 6 divided by 36. I'm just going to leave it like that. Okay, next option. So if you win, that's awesome. If you roll snake eyes, not so often, awesome. You end up having to pay extra $2. So you roll snake eyes, you already paid 4, you end up paying 2 more. You end up with a negative $6 if you roll snake eyes. Thankfully, there's only one way to get a pair of snake eyes, which is 1, 1 out of the 36 options. So that's very unlikely. You're probably not going to get snake eyes, but it could happen. You end up having to pay a whole $6 just because you got snake eyes, which sucks. The last option, if you roll and you don't get either, well then you lose your $4, right? Because you don't get it back. They're not going to give it back to you unless you win. So that's the rest. So if you take out these 6 options and then one option there, that's 7. So you're left with everything else. So 36 minus 7 gives me 29 options left. Remember that complement rule? So if you take all these options, they're not losing. You know, this is losing bad, I guess. But take these options and take that out of 36, you're left with the rest, which is the 29. So that'd be my different probabilities. So here they didn't give me the probability distribution. If they'd given me the distribution, I could have just done it, but since here they didn't, I'm going to have to find it myself. But once I have the probability distribution, again, I'm just going to put it in my lists and then let the calculator figure out the value for me, that expected value for me. So I got 16 is the first option, I've got negative 6 is the second option, and negative 4, so a couple bad options. First one, thankfully, is 6 out of 36, that's okay. 1 out of 36, not, you know, is very unlikely, thankfully, because that's the worst option. And then 29 out of 36 is actually pretty common, so that sadly is going to be the most common thing. And it's also bad because I lose money with that one. So probably not going to expect a great expected value, but let's see what happens. So I'm going to do stats, calculate one of our stats. Again, list 1 should be the first one because it's my values. List 2 is the probabilities, percentages. That should be my list 2 for my frequency list. Calculate. And I can see the mean for this is actually negative 0.7. So this game didn't sound that great because of all the different ways to lose, but it actually is still a better game to play than that, you know, raffle we got at the beginning because this has a mean of negative 0.72. That's less than $1 losses, so that's not too bad versus the $2.83. This one was so much more expensive, $4 or $5 to play. And the chances of losing are pretty bad. They're like 97%. This one's not quite that bad, chances of losing. So this one actually was a better game to play. So if someone asks you, which game am I going to play? I'd play the dice game. Yeah, you can't win big bucks. You're not going to win, you know, $200. But you're probably going to lose less. That's what this is telling us. The losses aren't going to be as bad. Each time you play, you might lose a couple bucks. You might have a bad one where you lose $6. But most of the time, you're not going to lose too much money. Whereas this one, most of the time, you're going to lose $5. So this is actually a better game down here. Expected value is how people do that. And people use this for lotteries, for raffles, anytime where you can kind of look at the probability of a good payoff or that kind of thing. You can use expected value to figure out, like, is it a good payoff or not? How bad is the negative? And if you get a positive again, that's great. Do it over and over again because you're gonna make money. Okay, last little thing to talk about in this section is significant results. So we've talked about significance before. Significance, remember, is things that are kind of unlikely. So we say if it's significant if it's unlikely. If it's highly unlikely, it's significant. So So in statistics, what this means for us is you go out do a survey and you get a result you didn't expect, it wasn't very likely, then that means something. It's important. It's significant. Um, so that's one reason why we use probability in statistics, is you have to assess what the likelihood of an occurrence is. So if you go out and you do a drug trial and you do a test with 50 patients, you have to figure out first what's the likelihood of these people recovering without the drug. And if you know that, then you can kind of look at it and say, okay, well, based on that, this many people recovered. Now I can see if that was significant. So if you say 10% of people are just going to recover on their own without the drug, and it turns out you're after people took your drug, 12% people recovered, you're going to say that's not that significant. That's not important because it's pretty close to 10%. But the more extreme the change is, the more likely you can start to say, yeah, my drug was important. So significance, it's all about things that are unlikely. We don't expect them. So we say something is significantly high if the probability of that much or more is 0.05 or less. This is the same thing as saying 5% or less. So the chances, the probability is less than 5%, 5% or less. You say that's significant. I didn't expect that. Oh yeah, 30% of people got better with my drug than the 10%. Maybe that's enough to say, hey, that's actually way better than I was expecting. We didn't know how much this drug would help people, and it looks like it's working great. Or maybe it's even better. Maybe it's like 60, 70%. That's important. So if the probability of that much or more is less than 0.05, then it's significantly high. Now, conversely, we'll say something is significantly low, not because the probability is less than high. Remember, the probability is going to be low in both cases. The probability is going to be 0.05 or less in both cases. But the difference is now, instead of looking at this much or above, we're going to look at this much or fewer. So we're going to look at the probability still. We're going to say the probability of getting that value or less is 5% again. So this is still 5%. So the difference might be between, like I said, the drug test where we're looking for people to get cured versus like maybe we're looking at a side effect test. You're looking at what percentage of people that got the side effect. Well, then you want it to be small, right? Because you want less people to get the side effect. So then you might be looking, is that significantly low? Because if you can show that the percentage of people that got the side effect was really low, then you can say it's significantly low, that it's not likely, and then you can say that side effect doesn't really affect people. It's not really a true side effect for this drug. So that's what that's showing. Okay, so let's just look at this chart and use that. So first off, we want to find, okay, so the chart below gives the probability distribution of random variable x, the number of boys in a family with up to 4 children. So it's the number of boys with up to 4 children. Find the probability that 3 or more are boys. So 3 or more. Well, you can have 3 boys or you can have 4 boys. That would be 3 or more. So that probability, well, you just add up these two, right? Because those would be the only two probabilities for 3 or more, 3 boys or 4 boys. You can't do more than 4 because there's only 4 kids in the family, right? So you can have 0.25 or you can have 0.05. So for 3 boys or 4 boys. And that adds up to 0.30, which is 30%. And that's actually fairly likely, right? 30% is pretty high. So it's actually a 30% chance that they're going to have 3 or 4 boys in the family. That's pretty high. That's so high that it's not significant. Remember, it's only significant if the probability is low. So this is not significant because it's too high. We're looking for less than 5%. This is greater than 5%. And so it's not small enough. The chances were too high. I have a 30% chance. That's 1 in 3 families are going to have 3 or 4 boys out of their 4 boys or 4 children. So that's not significant. We don't really care about that. That's not going to be just too much of a surprise. So if I go out there and do a survey or pick a family at random and I get one with 3 or 4 boys, I'm going to say, I expect that because 1 out of 3 that had 3 or 4 boys. What about if we say all the children are girls? Let's find that probability. So the probability that all the children are girls, well, the only one that's all children are girls is going to be 0 boys. That's the only option. This option is all girls, so all girls. And that's the only one. 1 boy, 2 boys, that doesn't count. So this probability of 0 is 0.05, which is okay because we said that much or less, or that much or more, that much or less. So 5% is equal to, that 5%. So yes, it is significant. It's a low enough chance. So in this case, again, here we're doing significantly low. So that's why we're looking at 0 or less. We're looking at 0 or less because we're doing significantly low. Versus the last one, we do significantly high, and that's why we did this much or higher. Versus this one, we went that much or lower. You can't do any less than 0, so it was, that's why when we just looked at that one row. But that's the difference. So again, high versus low just tells you which way you're going to go. So if you're doing high, I'm going higher and higher numbers, so 3, 4, and it's a little backwards because the chart's upside down. And this one is low, so I'm going 0 or less. So that's how I do that. But again, the significance is all about the probability. Is the probability less than 5%? Excuse me, I sneeze. If it's equal to or less than 5%, then it's significant. Okay, and that's 5.1. That's that section. We do have one more section for chapter 5 where we're tying probability and statistics together. That's the last section before the unit 1 exam or the first exam. So the material in the first exam will be covering chapters 2 through 5. Like I said at the video for chapter 1, that stuff in chapter 1 is a lot of definitions. I'm not really going to test you on that specifically on the exam. You should know those definitions because we used them throughout the rest of this section. But the test will really cover chapters 2 through 5. All right, that's it for today. I'll see you on the next one.